Okay, so skip ahead just a little bit to do this one. Should be nothing new. We've done plenty of vector problems here. Question part A says, what's the net force in unit vector notation? Well, F1 and F2 are already given to you in unit vector notation, so just add up the x's, add up the y's. Stick an I on for x and a j on for y. We're done. How do we do part B, though? Good. It's asking you for acceleration. So, of course, we know F equals ma. And we know the mass. The mass is just 1. But what is the force you plug into that equation? Good. You've got to find the net force. This is the net force in unit vector notation, but you do have to sketch it out, figure out what your net is overall. So we got 1 to the right, 2 down. So 1 squared plus 2 squared, square root of that, you're square root of 5. Very good. Okay, so that's our net force as far as the magnitude goes. So square root of 5 equals A. Not 1 times A, but there you go. But it did say direction, so whichever way the net force is acting, that is the way it's going. That is the way it's going to accelerate. So you do need to do your inverse tan. 2 over 1, find that angle. 63 degrees, and we'll use Wes's south of east. Or subtract from 360. Although this is really just another vector problem anyway. Free body diagram is pretty much already drawn for us. A hockey puck having a mass of 0.3 kilograms slides on the frictionless surface of an ice rink. 2 forces act on the puck as shown below. And they give you the magnitudes. Determine the puck's acceleration. All right, well, I ultimately am going to have to get acceleration from what formula? Yeah, F equals ma. I know the mass, again, but I've got to come up with a net force. So sadly, this is a components problem. I do need to break these down into components. So you guys got calculators, help me out. So this is going to be a 30, 60, 91. So F2. So yeah, you guys should be able to tell me now. Opposite my 30 degrees. This is, yeah. If the hypotenuse is 8, the x component is going to be 4. Okay. That's a good one. We see in the multiple choice a lot. So this is 4 square root of 3, which what is 4 times square root of 3? I don't know.
4 times
6.9.
Okay. All right, now do the other force. So I don't have any tricks for a 20-degree angle, but our hypotenuse is 5. I've got an angle of 20.
the x is 4.7.
The y is 1.7.
The x is 4.7.
Yeah, not necessarily. X is 4.7, and the y is 1.7. Okay. So I found all my components. I guess throwing a negative sign here only. And now that I found all my components, now I can find my net force, because that is what I need for this equation. So add up your x's, add up your y's.
Teachers, pardon this interruption. Juniors that are applying for the junior leadership of Peters County need to report to the media center with your resume now. that juniors that are applying for the junior leadership.
Oh, I did. Sorry.
Need to report
That was why.
to the center at this time with their resume. This is only for juniors that are applying.
Oh, I could do this all in my head. All right, add up the x's, add up the y's.
And now I have to do that.
Now you do Pythagorean theorem.
Mm.
10.2?
Yeah.
Give me the angle.
31 degrees.
Thank you. Okay. All right, a lot of work just to get the net force, but now I can plug that in just for F equals ma. So 10.2 equals the mass of 0.3 times A. So divide that, and A would be 30.
33.84.
Meters per second squared at same angle as the net force. Got to be going that way. 31 degrees. Okay, that's another good vector one, but I really want to do the next one since that will help with a good free body diagram. All right, we have our traffic light set up like so. It has a weight of 125 newtons, and these cables make these angles. Find the tension in the cables. And I'll throw on here weight of 125, maybe. You're going to need a little more room for this one. So if we did make a free body diagram for our little traffic light, based off of this picture, what are the forces acting on it? Weight down, yep. And specifically, which tension? Tension 3. And that's technically it for the traffic light, the way it's drawn.
But that means that the tension
So,
is 125.
so exactly. So I know tension 3 equals weight equals 125. But that doesn't even incorporate these other ropes. So what I would do now is I would do a free body diagram for this intersection point. So this point of all the cables pulling on each other in different ways, my free body diagram is pretty much as drawn here. I've got T1, T2, and T3 down, like what I did in green. And I'll go ahead and break them into components, since these are obviously at angles. We got T2, try to make this one green. And I don't know what T2 is, that's the point. I'm trying to find what T2 and T1 are. I've already figured out T3, but I'll call that T2X and T2Y. And I'll do T1 in green, so we've got our hypotenuse.
T1 y equals T2.
And you could have drawn your triangles out here. We just would have been a little more clever about the angles. I just want to leave the angles where they were. Okay, so I've got a free body diagram drawn. I drew my components, so that means I really should not be using T1 and T2, but the components of them. And now it's still, so it's a constant velocity situation. So what is true? Let's go with the left-right direction first.
Left to right direction.
This way. What must be equal?
T1x plus T.
Good. Is there anything else left or right? Nope. All right, how about up, down? What's true?
T1 Y plus T2 Y has to be equal to T3.
Very good. Both of the y's are acting the same way. They're both going up, supporting the weight of that thing, and it should equal T3. All right, so since I had a good diagram, I was able to come up with the equations I needed. Now it's just algebra. I've got to figure out what exactly to plug in, what trig I'm using. I realize again, ultimately, we're not really trying to find for T1x. I do want to get the answer for T1. But that should be easy to come back and do since I know this angle. All right, so what can I plug in? T1x is really what? How would I relate that to my hypotenuse here? How would I relate it to T1 and this angle?
T1 times the
Cosine, okay. So T1x is T1 cosine of 37. And that would equal T2 cosine of 53. Again, I'm not worried about positive and negative signs anymore because I've already taken into consideration their directions when I set up this equation in the first place. I said left equals right. I'm just dealing with the magnitudes. I know the magnitude left equals the magnitude right. This is a 1. Not a very good one, but a 1. All right. Now let's break down the y a little bit more. That's just going to be sine. So T1 sine of 37 plus T2 sine of 53 equals, I'll go ahead and plug in 125. Now what do? I plugged in what I knew. I've gotten this far.
You like subtract the T2 cosine 53, make it set equal to 0, and then do like substitute or elimination.
Yeah, we need to do some substitution. This is how a lot of your problems will work out. You've got an equation for sort of left-right, an equation for up-down, and you'll need to solve for one variable in one of them and plug it into the other. So I couldn't just answer this with the x direction, too many unknowns. I couldn't just do it with y. So I'll start with this equation up here, and we'll say that T1 equals T2 cosine of 53, and I'm just, not subtract, but dividing by, well, not that you said subtract, 37. And in fact, you guys could go ahead and do that part right now and kind of clean this up a little bit. What is cosine of 53 divided by cosine of 37?
0.75.
Oh, that is very convenient.
It's not exactly how that rounded off.
Oh, well.
Rounded off.
All right, so that's helpful. Now I can get rid of all the T1s by plugging this in here. And then I'll have this equation just in terms of T2. Kind of a math mess here, but we can power through. All right, so for T1, I'm plugging in, what? I had a solid like 4 minutes. Darn it, okay. Okay, so now it's going to seem a little weird since I was about to hear yesterday. Now we're just going to do a random recap of this problem in the middle. But what we were doing 2 days ago before the bell rang on us was we were trying to find the tensions in all of these chords. We were able to draw a free body diagram for the light itself, and we knew the weight of the light down had to equal the tension up. So we already knew tension 3 was 125. That was given. Then we drew a free body diagram, which is sort of what I got going on right now. Come on, give me pink. For this spot right here. So for this spot right here, I've got tension 2 going that way, tension 1 going this way, and tension 3 pulling it straight down. So tension 3 is at least in the y component. So I know that anything up should equal T3. So that's what we wrote in the blue up here. T1y, so just the y component of T1, not T1 itself, but the vertical component of it, plus T2y should equal 125. So we knew that had to be true because this is still, not falling. And then similarly, we could say T1x had to equal T2x. And we're good at drawing triangles, so we can use our trig to know, where to throw in our sines and our cosines. So T1x in terms of T1, this side up here, so that would be 37 cosine, adjacent side. So T1 cosine 37. So the blue is the vertical, the red is the horizontal. Pick whichever one you want and solve for something. Solve for one variable. Solve for T1, solve for T2, doesn't matter what you pick. I just went with this one to solve for T1. So I just divided this cosine over. Simplified this a little bit, put this in the calculator, and that turned out to be 0.75. So then I plugged all that in for T1 up here. Came down here, cleaned it up, and we ended up getting T2 is about 100 newtons, 99.8 newtons, and T1 was 75.2 newtons. Another way of doing this would be to make a nice vector diagram. And we're going to use the force tables today for a little lab, which you guys maybe used last year. But in this situation, and when we use the force tables, everything should be in equilibrium. Everything should be balanced. So these forces are balanced right here. So a vector diagram of all these forces added together, would look like what? Well, I could start with T2. T2 clearly goes this way. And I got my 53 degrees here. Alternate interior angles. All right, and then from there I could sketch T1, and that's 37. And what do we kind of notice about 37 and 53? Yeah, they add up to 90, and that is nice. Because if that's 37, that's 53, that gives me a lovely right triangle. And T3 should be straight down, and I should end up right here at the origin. How do I know that when I add all these vectors together, head to tail, I should end up at the origin? Because it's not moving, it's balanced. It's still. So even though it's being pulled, this point's being pulled in 3 different directions, it's in equilibrium. So T2 plus T1 plus T3 should just get me right back to 0. The net force is 0. So how is that helpful? I can sort of use Pythagorean theorem, but I still don't know all my sides. I at least know T3 was 125. But I could come up with this equation, 125 squared equals, T1 squared plus T2 squared. Which is only slightly shorter because you're still going to need at least one other equation. If we did all this work in red, maybe we could have gone from here to this equation. But I still do need 2 equations because I still have 2 unknowns, T1 and T2. So either way, that will work out. Questions on that problem? Okay.
T1 and T2 at the bottom of the side, is that just a y component?
No, this is the actual, hypotenuse, the actual tensions, not a component at all. If I wanted to check the components, like you could plug these in right here.
Why couldn't you plug it into the T2 right?
Oh, you could. I'm just saying before I got here, as another way of getting those answers. But you could check. I mean, it's not a bad idea to check that these fit into any of the equations you wrote already to make sure they're true. So this is a good equilibrium type problem. We had a good free body diagram. Now we'll do one more example problem. That's a good net force problem where we actually are accelerating. And that's going to be the pulley one here. Okay, this is kind of the free body diagram thing you drew for us the other day, Zach. So find the magnitude of the acceleration and the string tension for an Atwood machine in which mass 1 is 2 kilograms and mass 2 is 4 kilograms. So this is simply our scenario. If this mass is bigger, obviously it's going to accelerate down this way. So we've already got our 2 separate free body diagrams. And we can say that the tensions in the string are the same. There's no other object in the middle, no extra penguin or other thing being pulled. So the tensions are the same magnitude. Well, they actually are both going up too, and same direction. So let's work off of our little free body diagrams here. And I'll try to make this maybe the blue one. Whoa. Okay, so I already got the free body diagrams. This would just be another way of writing weight 1 or weight 2, just mass times gravity. So for the circle, what must be the net force? Think about the free body diagrams from the other day. Based off of the variables, not a number at all. Just good. This is winning out. Tension's the bigger force minus weight 1. And if we have a net force, it's almost always handy to remember Newton's second law, which would be what here? Well, what is Newton's second law? MA. But we just have to be a little careful that we're making sure to use, this mass, not that mass. We're talking about the mass and acceleration of this object, just that object for the time being. All right, so we'll plug in what we know. We got T minus 2 times 9.81. And mass 1, again, was 2A. Okay, now let's do the same exact thing for the square. According to the drawing, the net force is equal to what? Good. This time weight's bigger, so weight 2 minus tension. And of course, we also know Newton's second law, MA, but make sure we're just plugging in mass 2. So this time we've got 4 times 9.81. What is it? 39.4. Okay, where do we go now? What are we looking for? Looking for acceleration and tension. So we find either one first. You've got 2 separate equations. Both have tension and both have acceleration in them. So just pick one to solve for and plug it on into the other. I'll solve for this one because I just got to add the 19.6 over. But then you want to put that tension in here. That pretty much fit. Somebody tell me what you get for A.
3.27.
I'll tell you if you're right. Yes. So, notice this is minus t. Be a little careful of your distribution. Make sure that negative sign gets distributed there. But 3.27 meters per
Where's closest?
right across. Once you know the acceleration of the system, which, how do you know that makes sense, by the way? It's not ridiculously wrong. It's certainly possible. What would be a ridiculously wrong acceleration?
320.
Yes, because that's much bigger than,
3.67.
and, yeah, it's bigger than, it wouldn't be bigger than 9.81. We should know that it can't possibly be faster than free fall, because this weight's sort of holding it back. Yeah, so that would be a good thing to note. All right, so we've got our acceleration, then just plug it back into your favorite equation and solve for t. I'll plug it back in over here. .16 newtons. Okay. Ta-da. Now, using F equals ma as an equation would only be relevant when your system's doing what? Like, we didn't use F equals ma in the streetlight problem. Yeah, if there is an acceleration. You would only use that for an accelerated system. If it's not, then F net equals 0. Okay. The end.